and welcome to today's webinar. My name is Tyler Reid. I'm the Manufacturing Application Manager here at GoEngineer. And over the next half hour or so, you and I are going to be discussing 3D printing alongside hollow composites. The creation of hollow composites, and when I say composites, I mostly refer to carbon fiber, but it also applies to things like fiberglass or Kevlar fiber. Parts that are hollow tend to trap the tooling. Hollow parts are created by either wounding them or wrapping them, molding, or laying up a carbon fiber sheet or strip or mat, wrapping it around a shape and curing that. You create a hollow part by then, after the curing, removing that shape. And in a lot of cases, that shape would become trapped after the carbon fiber is cured or hardened. In the case of something like a tube or a cylinder, that wouldn't really be the case. But more complex shapes can become trapped, and that's where the problem lies, is how do you deal with that trap pattern? Typically, how it's been done is you create a core made from really puzzle pieces, separate pieces of the core that can come out separate from each other. So you might have an internal part that's removed, and then the outer walls can then be moved and removed. Or you deal with a clamshell mold. And if you do a clamshell, then your parts typically have to be bonded after they're cured. So in the image that you see there, which is from Champion Motorsports, we have a few different examples from them today. You can see a fairly complex shape. You could create that shape individually, maybe the three pieces there, using clamshell molds. Or we can create them all as a single piece using the FDM pattern. So the problem with the clamshell molds is that you can get the geometry, but you have to bond the two pieces or the two halves together later on. And that bond, interrupts the integrity of the matrix. And the matrix is where these carbon fiber parts get all their strength. So we want to try to avoid that. It's also unsightly. So in a lot of cases where the visuals make as much of an impact or is important to the customer, especially like in this automotive example here, we want to avoid the seams because it's extra labor and just unnecessary. So the solution here are FDM soluble cores. FDM soluble cores, I'm sure some of the people here have heard us talk about it before, but we haven't really gone in depth into it before. So that's what we're aiming for here today. The whole idea here is that we're going to print the pattern that would be trapped directly in a soluble material. In our FDM machines from Stratasys, we can print in soluble material, and that's typically done as a support material. So the 3D printing process, just in general, normally requires a support material and a model material. And the model material is normally the end-use material. It's the ABS or the polycarbonate or the nylon. And the support material is there just so we can build overhangs and internal voids, and it's dissolved away later on. It's sacrificial. But within some of the software that we use, namely Insight, there's a checkbox that says invert materials. And if we check that box, we can actually print our end part, our goal part, in the soluble material. And then any support material that's needed would be printed in the end-use material, the ABS, for example. That is an option only in the Insight software. So in order to check that box and have that box available, or really to be able to print an end-use part in soluble material, you're going to need to be in a machine that uses Insight, which is the Fortis 250, the Fortis 380, 450, and the 900. So the production level machines typically. If you're not into one of those machines and you're still interested in this, hang on, because I might have some ideas for you that we're going to be talking about. But in general, if you're going to print the soluble core, you're going to be at the Fortis 250 or above. So what are some of the benefits of the soluble cores? Well, these are some numbers that Stratasys came out with from their dealings with a variety of different customers, and we'll see some of them in the slides later on. You have a lead time savings and cost savings. So the FDM cores, we can produce them quicker and we can produce them cheaper. Tied into that is reduced labor. So there's less tooling involved if you're printing something directly as opposed to creating like a foam cast or something like that. It's also hands-free. When I create these cores, I print them typically overnight. So I'm out doing other things. I come back the next day and I have a pattern here. We can also do better parts because we have more design freedom. We can start to integrate hardware. We can do single pieces where you used to have to do multiple pieces. We have a lot better control over the surfaces, etc. And because there's a cost and time savings, it's really easier to modify or iterate the design because there's no tooling investment. And we have improved consistency over like a molding option there. So where does it make sense to dive into a soluble core situation? It's typically going to be a small quantity and high value situation. So you need maybe less than 100 parts. Those might be functional prototypes. And if it is a functional prototype, it makes a lot of sense to go through FDM because, again, it's easier to iterate. There's no tooling involved. There's no machining involved. We can print 3 or 4 different designs in the same day altogether if we need to. And also custom production parts. Custom in terms of it might be a quantity of 1 or 5. And that's where we see Champion Motorsports coming into play a lot. What are the part characteristics? So we meet maybe the correct criteria above. When does it still make sense? Complex or very intricate designs. So we're obviously not going to be printing a cylinder alone and doing a soluble core on that because a cylinder wouldn't be trapped. So more complex and intricate designs where you would have trap patterns. If you need a hollow or undercut part, any part that's going to be undercut kind of ties into the complex situation there. If it's a design requirement that the part needs to be seamless, it might make sense. And also we need high quality internal surfaces. You'll notice a lot of the examples that I show today are of manifolds and piping where there's going to be internal flow. And it makes the most sense in those situations because the internal surface is actually the surface that matters most in order to maintain good flow qualities. So what are our material options? We keep talking about soluble materials. What sort of materials are we talking about? Well, the first is called SR30, and this is the Stratasys standard soluble support. It is a soluble support that's used on the ABS materials, ASA, most of the non-high heat or high mechanical strength materials. We can use this in temperatures up to 180 degrees Fahrenheit. That's the stated heat deflection temperature, and that's a temperature that you would want to stay at or under during the curing process. And if you're going to put this in an autoclave, you'd want to keep it at or under about 80 psi. The next option here is SR100. SR100 is going to be the stronger, higher temp, but still soluble support material. It's good to 250 degrees Fahrenheit, but the pressure is still the same. You don't really want to go above 80 psi on the pressure if this is in an autoclave. Both of these materials can be vacuum bagged and pulled full vacuum, but if it's in an autoclave, keep it at or under 80 psi. The last option here, I'm kind of cheating a little bit, because this isn't soluble, but we can still create hollow composites from it. So this is a high temp, non-soluble support. We use the S1 material with our Ultem materials. It's not soluble, but we can embrittle it with acetone. So instead of dunking this in our wash station or our ultrasonic bath, we would actually pour acetone or paint acetone onto the support material, let it soften, and then we'd break it out mechanically, pliers and whatnot. The benefit of doing this, it's extra work to get the core out, but we can have cure temperatures up to 350 degrees at ambient pressures. Or we can go up to 300 degrees Fahrenheit and 100 psi in an autoclave. All right, so going back to what I said a couple slides before, if you do not have a Fortis 250 and you can only print in ABS, taking a route similar to this might be an option. I haven't tried it yet, but I want to, is creating a core out of ABS, wrapping it, vacuum bagging it, curing it, and then embrittling that ABS with acetone or some other solvent, and embrittling it and kind of mechanically breaking it out. That's definitely an option. I'm going to try it. I haven't yet, but it works with the Ultem support. All right, so we're going to look at a few examples that I pulled from Stratasys and the net, and then we're going to look at examples I've done here at GoEngineer. So this is a wrap core example. This came from McLean Anderson. McLean Anderson is a composite mandrels company, and they do a lot of wrapping like you see here. And I showed it mostly because we see a lot of layup but we don't see a lot of wrapping examples, so I thought this was pretty interesting, and the shape is obviously interesting. You can see that's kind of an uncoated pattern. Here's some more examples from Champion Motorsports. Champion Motorsports has been working pretty closely with Stratasys and been pretty vocal about the benefits that they have seen going to the soluble support. They have a good video on Stratasys website where you can hear actually from the engineers talking about the process that they go through, the benefits that they see, and where it makes the most sense to them. You can see example on the left, very oddly shaped piping. That's typical inside of an engine bay where you're working around other components and inside tight quarters. That core that you see there, it's an SR30 core and it's uncoated, but it has been sanded and deburred. And that's going to give them the best internal surface. These guys do use both internal and external tooling. I don't have a picture of the external here, but I did see it in the video. So we have an FDM core for the inside, and then the external, it looked like a fiberglass tool. One thing to notice here is that that core is uncoated. It's the white, which is just the material color. But in their video, they do talk about coating or sealing these. And in some of the examples that I have later on, example photos, you might see why that is a big deal. On that Porsche motor on the right-hand side, we see some intake manifolds. We see some air scoops, we see some piping. That's all done through the FDM process. Here's an example of a hybrid composite. This comes from the Missouri University of Science and Technology. A lot of the examples that I found just while Googling the topic, 3D printing and hollow composites, came from university FSAE teams. And again, this is another intake manifold. You might have noticed that the automotive industry is pretty well represented in this application. You have the FDM core on the left. You have the finished product on the right. Notice that we have some aluminum parts integrated into the mold here. So this is the idea of being a hybrid composite. It's not going to be just carbon fiber. You're going to add some aluminum, or in other cases, maybe some 3D printed materials to the pattern before you wrap it and cure it so they can be embedded. We saw some similar examples in some of the previous images where we had embedded bungs or mating surfaces, stuff like that. So pretty common. Here's an example from Northrop Grumman. This is a high temp tooling using the S1 support. I like this example because it's very physically large. I put the size there. It's 2 feet by 2 feet by 3 feet core size. Notice that the tool is hollow over on the left there. It's basically just a shell part. And that's going to be important when it comes to actually break out the mold. That's going to, minimizing the amount of support material that you have to remove makes sense, whether or not it's soluble or breakaway, like it is in this case. Some of the unique things that they did with this is the higher temperature curing, and it's also got a 2-stage cure. So whereas I said the SR30 is good up to 180 degrees Fahrenheit, and the SR100 is good up to 250 degrees Fahrenheit, the S1 can go up to about 350. The two soluble materials can actually go through a 2-stage curing process as well. So the initial curing process might be up to 180 or 250. That's going to cure the composite enough so that if you go to a second curing stage that's higher temperature, the composite's not going to change shape even though you might lose some of the support. So that's totally possible. And that's kind of what they did here. They did an initial cure, 266 Fahrenheit. That was in an autoclave, but they didn't publish the pressure under 100 PSI. And then they did an out of autoclave post-cure at 356 degrees Fahrenheit. And that must have been a requirement of the resin. Obviously, it's an aerospace grade resin. Most of the resins that I've seen and that I've worked with don't cure at this high temperature. I've never encountered the need to do an S1 support. But the neat thing here is that they were able to maintain plus or minus 1 millimeter accuracy in a fairly large bounding box. Here's some of the process steps that they went through. So you can see it's an out of autoclave layup over in the top left. They wrap it, they vacuum bag it. There isn't a picture of the autoclave, but it goes through the autoclave process, and then they use acetone to break out large chunks. It's a little bit different process than what I've been doing here in the office, which I'm going to show you. I don't really have access to an autoclave, so I use vacuum bagging and wet layup. And then we use the ultrasonic tank to clean out the water-soluble material. All right, so the next few examples are ones that I've done kind of in preparation for this webinar. And I call it do-it-yourself because I've done it basically in my garage. And I like these sorts of examples because it makes the topic very approachable to people in R&D facilities or looking to investigate it on their own. So these were the first two parts that I did. They're basically handrails that came from a NASA file, handrail from the International Space Station. NASA hosted a design contest on the website grabcad.com to come up with different clamps for this rail. And you can see an example of the clamp, one of the winning clamps there. So the first part I made was on the left, and I just printed an ABS, cylinder. So not the best example of a soluble core, but it was my first time doing composites in several years, so I wanted to try something, just practice, and it came out pretty well. The second part that I made is the one that's in the clamp there, and it was a hollow part. It was SR30, and it came out pretty okay. It washed out just fine. Some difficulties clamping the part. It might be hard to tell from the images here, but the one on the left, I vacuum bagged around the entire part, and it came out perfect cylinder, but I didn't account for the thickness of the carbon, so I couldn't clamp on it because my part was a little bit too big. I measured that part. I figured out how thick, 3 layers of carbon would end up. I scaled down the part. I wrapped it again, but since in the first part, when I vacuum bagged around the entire part, I had trouble sealing the vacuum bag, I decided this time I'll lay down a piece of plastic that's flat, and I'll vacuum bag the part against the plastic. And it sealed great, but then I had some kind of corners. So you can see that part on the second part's not 100% cylindrical. So even though the size is right, I still had trouble clamping it. Lessons learned. So I thought, okay, those are good test parts. I'm going to step up the game here and try something pretty difficult. I wanted to create a carbon fiber airfoil. So in SOLIDWORKS, I created the part on the left. And my idea here was that I would print some spars out of ABS, print some middle pieces out of SR30, and I would wrap it all up and dissolve away just the support parts, and I'd end up with some spars internal to the wrapping. So that was the idea here. You can notice that these are all designed to be printed independently. I've got some mating features between the parts, and these were printed independently. If I had stacked these together and tried to print them, I would have ended up with a lot of excess support material. Here's lesson number 1. Consider how your core parts are going to be supported, right? Just because we're printing out a support material doesn't mean we can print any shape. The support material potentially will still have to be supported itself, and the machine will use model material. What you're looking at is the bottom of one of my support. Going back to this page here. You're looking at the bottom of one of those, and you can see some model material trapped in there. I had to manually remove that with essentially a Dremel. And it wasn't a big deal in this case. I was able to get it out fairly easy, but that's something to consider. If you have an extremely complex casting or pattern that you want to create, you're going to have to consider how it's going to actually print. Where will the quote support material need to be, and how are you going to remove it? So if I had changed my design a little bit so my support material didn't move up into the part, especially in small areas, it would have broke away a lot easier. So lesson number 1. Here's the part all put together. You can kind of see the scale there. This is about 19 inches tall. And I used super glue to bond the pieces so that they wouldn't move apart while I was doing my wrap. I wanted some sort of bond, but I didn't want it to be incredibly strong. So here's the materials that I needed. And this is just standard vacuum bagging stuff. I've got a vacuum pump. I obviously have my carbon fiber. It's a 2x2 pattern, and I did 3 layers on this. I've got my vacuum bag, my release material, my breather material, and my tape. Here's a picture mid-vacuum bagging. So this time I learned my lesson. I vacuum bag around the entire part. Notice in my vacuum bag I have some creases. That's important. So up in the upper left-hand corner and the right-hand corner, you can see I've got some creases in my tape line. That gives you extra space for the vacuum bag to kind of creep into every nook and cranny that you might have. So the resin that I use is just a standard epoxy resin. It had a cure time of about 4 hours, so I kept a vacuum on it basically overnight. When the parts came out, they didn't look exactly like this. This is the part after I've trimmed the ends. So this is the part post-cured, but the ends have been trimmed, and you can see I was a little bit dirty in my trimming on the ends here. But you see on the left-hand corner, or in the left side, this is the top of the airfoil, and I see salmon right there. I'm just going to say it. It looks like a piece of salmon, but it's carbon fiber. On the right side, you see in the upper right, you're looking at the large end of the airfoil. You've got the embedded spar there, and we can still see the support material inside the white. And then on the bottom right-hand corner, we see the top, the small end. All right, so this is the bath setup that we used. It's an ultrasonic bath from a company called Omega Sonics. This is the best way to remove support material in general. It's much better than the standard wash station, where the wash station just has heated water alongside detergent that's kind of circulated. This is heated and ultrasonic. All right, so this is the setup that we used in this case, and it actually might have hurt my sample, which I'm going to talk about here. So notice this next image. This is after I took the part out of the bath, and it's the bottom side of the airfoil, the large side. At first you look at it and think, oh wow, the support material is gone. That's perfect. And then you remember that there's supposed to be a spar there. So I actually didn't get a good bond between the spar and the composite. And that's something that I'm going to have to work on coming up here. I don't know what caused that. Either I didn't prep the surface enough on the ABS and I didn't get a good strong bond, or I kind of suspect that the ultrasonic cleaner worked against me. So the ultrasonic cleaner helped the removal of the support material, but it also might have helped remove the ABS from the composite. So I'm gonna have to do some more testing here. And when I learn something, I'll probably update the comments on the YouTube video so people know what I found out. So for right now, I'm going to be trying two things. I'm going to try to prep the surface better, like really roughen up the surface on the ABS, and make sure I pre-coat the ABS with some resin. And also I'm going to try to avoid the ultrasonic cleaner next time, where I have an embedded part. And also this picture is a little deceiving because if you look straight on inside the cavity, there's still some support material here. So this is lesson probably 3 now, is you need to seal your support material, all right? And print it as sparsely as possible. So we're looking about 6 inches into the part. There's start to be some more support material in there. It was all removed up to that point. And there's 2 things going on here. I printed my support material too dense. In the software settings, I use what's called double dense, where I should have used as sparse as possible. So reduce the amount of material, or made it completely hollow, which would have been probably even better. And also, you got to seal your support part. I had a lot of problems with the epoxy that's used in the composite adhering to the outer surface of the soluble core. And it goes back to the Champion Motorsports example where they talk about and they show themselves sealing that part either with some mold release or a gel coat or even some Vaseline, sealing it so that you don't get a strong bond, because it will melt away, it will dissolve away, but the ends, the kind of outer skin will come away in chunks, and it's really just epoxy. So there's lesson number 3 there. Here's the top of the part. You can see where I didn't quite lose the spar, but I did get some delaminating between the two. So the same thing happened on the top with the small spar as it did on the bottom. And again, that goes back to either, kind of promoting the bond between the composite and the ABS, and also maybe thickening up the composite as well. I only did 3 layers, and at 3 layers, the composite's still quite flexible. So I think if I did something a little bit thicker, it might also be less prone to pull away. Embedding parts that are printed, a little bit difficult. As far as the water soluble portion, that wasn't adhered to the outer skin for my own fault, it worked great. So kind of recap the lessons learned here. Definitely seal your soluble material for best results. You need to have a barrier between the resin and the support material, and that's going to help it release and dissolve. And again, that might be mold release or gel coat or something like that. Consider the support needed for the soluble build. You don't want to have difficult to remove model material supporting your pattern on the print tray, because you're going to have to remove it, and you're going to have to remove it manually because you can't dump it in the tank like we normally do. Print your soluble parts as sparse as possible. I printed mine double dense because I was worried about the compressive forces from the vacuum stage on my part, but I went back and I kind of looked at the math, and that was pretty much unfounded. So next time I do this, I'm going to either create a hollow part and just print an outer skin, or I'm going to use the sparse command inside, and then maybe go in and manually make it even a little bit more sparse. I'm going to try to sparse it up as much as possible. Insoluble cores could be possible. So this is a point where we might be able to use ABS in this process. It's just going to be, it's not wash away. It's going to involve solvents and mechanically removing the core pattern. But it might be possible, especially for parts with easy access to the core, parts that we can get in with pliers or something like that. So if you're in a bind, you only have an ABS part, I think you can still do this. Surface details need research. So you might have noticed in my airfoil model, I had the GoEngineer logo in my top spar. That didn't even come close to showing through. So I had that debossed into the part, about 20 thou. That's either going to need to be deeper, or I might have a part that goes between the layers of the carbon fiber that embosses the text or raises it up. So I need to research into that a little bit. And hybrid parts. So my last part, where I wanted to keep some non-soluble parts embedded, I need to promote a better bond between those. That might be roughing the surface up or pre-coating the insert with some resin to make sure it's got enough resin. Possibly avoiding the ultrasonic bath. The ultrasonic bath is much more aggressive on the parts, and that speeds up the removal of the support material considerably, but it also might affect the bond between, in this case, the ABS and the composite. And also, thicker is better for the composite skin. Thicker is going to be stiffer. Stiffer is going to reduce the chance of it changing shape or pulling away on us. We can create very accurate parts, like you saw in the Northrop Grumman part, plus or minus 1 millimeter accuracy in a build space of 2 by 2 by 3 cubic feet. And in the case of Champion Motorsports, they've got parts that are accurate enough to be installed by their users without any sort of modification. So we can get accuracy there, but it's going to take some careful usage of the composites. So that's about all I had for you guys here. I want to thank you guys for joining. I really like doing this one because I got to get my hands dirty. The next webinar is coming up in 2 weeks, and I'm going to be covering urethane castings. And this is also going to include some of my own castings. If you're watching this on YouTube, thank you for joining. Definitely check out our other videos, and thank you for watching.